Similar to the first step of sp3 and sp2 hybridization, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Mixing the 2s atomic orbital with one of the 2p atomic orbitals causes two new degenerate energy hybrid orbitals. The shape of the new sp hybrid orbital is best characterized as 1 part s and 1 part p. As with all orbitals, think of these hybrid orbitals as three-dimensional shapes where you can find the electron 90% of the time. The sp hybridized carbon now possesses 2 electrons in hybrid orbitals and 2 electrons in the unhybridized 2p orbitals. When we superimpose both sp hybrid orbitals with the unhybridized 2pz and 2py orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. In addition, the electron density of the unhybridized p orbitals is shrunk to 1/3 of their size for simpler viewing. The 2 new hybrid orbitals attempt to get as far apart from each other as possible. Again, think of this as the orbitals attempting to minimize electron repulsions. Thus, they are oriented 180 degrees apart. Before we begin to show how the sp hybrid building block takes part in bonding, it is important to remember that the electrons in the unhybridized 2p orbitals have access to both lobes. Your instructor will often draw the sp hybridized carbon on the blackboard as shown. Again, solid lines are in the plane of the board, shaded lobes are coming out of the plane of the board, and dashed lines are going behind the plane of the board. Each of the 2 sp hybrid orbitals contains 1 electron capable of forming a sigma bond. The sp hybridized carbon is now capable of forming 2 sigma bonds and 2 pi bonds. A simple carbon compound that utilizes sp carbons is ethine or acetylene. From the 2-dimensional Lewis diagram, we see that each carbon forms 2 sigma bonds and 2 pi bonds. Thus, both carbons are sp hybridized. Starting with 2 sp hybridized building blocks, we can begin to construct the molecule in 3 dimensions by forming the Cc sigma bond. Next, the 2 carbon-hydrogen sigma bonds are formed, which affords the linear sigma bond framework for ethine. To form the second and third bonds between the carbons, called the pi bonds, we can imagine that the 2 pairs of adjacent parallel unhybridized 2p atomic orbitals overlap. When they overlap, the 4 electrons can be shared, allowing each carbon to attain full valency. The 2-dimensional Lewis diagram for ethine allows the chemist to view the gross connectivity of the atoms. However, no information is conveyed about the pi bonds. When a molecule is represented in 3 dimensions, we see that half of each pi bond is above and below a plane. An understanding of this electron density within these 2 pi bonds will become very useful when predicting reactivities of alkynes. To gain a better understanding of the 2 pi bonds, we should recall the actual shape of the unhybridized 2p orbitals. When we envision the actual shape of these orbitals, overlap between the adjacent 2p orbitals is possible, which allows for the sharing of these 4 electrons. However, it is very difficult to draw the molecule this way, thus you will often see the pi bonds represented in the abbreviated form on the right.